So related rates problems are generally word problems where I guess the real challenge is probably not as much actually doing the calculus. I would consider that like the last 1% of the problem, but it's parsing out the problem, mathematizing it, so like creating a notation, creating an equation that you have to deal with, figuring out what it is you need to solve for. Once you have all that down, then doing the actual calculus is no problem. That takes 1 second. All right. So you don't have to write this down, but this is just to give you kind of an example of what we're going to look at. So if we're pumping air into a balloon, you have the volume changing and you have the radius changing. Now they're going to be changing at different rates, but those rates are related to each other, thus related rates type problems. All right. So here's kind of the strategy that we're going to go through. I realize that 5, 6, and 7 are crooked. I did that just to annoy you guys. I guess 2 and 3 and 4 are also crooked in the other direction, and 1. All right. So the first part of the strategy is read the always condescending, read the problem carefully. But it does make a good point, which is we can kind of get ahead of ourselves in math sometimes and just want to read the problem and start doing the math as we go, right? Pulling things out as we go. It's important in these problems to actually read through it one time without writing anything down, just to wrap your head around it. Second, in a lot of these, you'll be drawing diagrams, so we'll do that. Third, extremely important, introduce notation. So assign symbols to all quantities that are functions of time. And I'll point that out as we do these. Fourth, express the given information and the required rate in terms of derivatives. So anything that's a rate, remember, is a derivative. A rate is a rate of change. A rate of change is a slope. A slope is a derivative. So this is where we're getting to kind of parsing out the language and introducing our notation in terms of derivatives. Then fifth, we're going to write an equation that relates the various quantities. And if necessary, we can use geometry to eliminate one of the variables by substitution. And we'll do a couple examples where that comes into play. We'll mostly be using the chain rule to differentiate, and that's because everything is going to be, when we're talking about rates of change, we're generally talking about them changing over time. So things are going to be functions of time. That's going to require us to use the chain rule. Finally, substitute the given information and solve for the unknown rate. All right. So here we go. Let's do a couple of these. I think we're going to do 3 of them today. So air is being pumped into a spherical balloon so that its volume increases at a rate of 100 cubic centimeters per second. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? All right, so we did step 1. We read through the problem. I'm going to sketch out what's going on here. So I have a spherical balloon. Here's its radius. I'm going to introduce a notation. We'll call its radius r. I'm feeling creative today, so I'm going to go with r for radius. Okay. The other pieces of information, they give us information about how fast the volume increases. So I'm going to say, all right, we're talking about volume of a sphere. So I'll introduce some more notation. V for volume. The formula for volume of a sphere is 4/3 pi r cubed. All right, but what they tell us, and the other thing I'm going to say is the balloon is increasing in size, right? It's expanding. We're filling it with air. So the volume is changing over time. So volume is actually a function of time. So I'm going to rewrite it like that. V of t is 4/3 times pi. And as the volume increases, that the balloon is expanding, so the radius is also going to be increasing. So radius is also a function of time. So 4/3 pi times r of t cubed. And so I just did that to indicate that both of those are functions of time. They're changing over time. So really, t is my input variable. All right. So now we have the equation that relates the volume and the radius. They tell us that volume increases at a rate of 100 cubic centimeters per second. So a rate indicates a derivative. So that means V prime of t is 100 cubic centimeters per second. And again, I indicated that, or I used that notation because it said rate indicates derivative, right? And the thing that we're looking for, how fast is the radius increasing? So again, they're talking about a rate. How fast is the radius increasing? So they're talking about r prime of t. And that's the thing I'm trying to solve for. That's the thing I would like to know. Okay. So we have v prime of t. What we're trying to figure out is r prime of t. We have an equation that relates v and r. So what we want to do with that equation is take the derivative with respect to time. So I'm going to go d dt, and this is where that chain rule is generally going to come in. So I'm going to take d dt of both sides of the equation. On the left, I just end up with v prime. The derivative of v is just v prime. On the right, we're going to have to use chain rule over here because we have r of t to the third power. So I'm going to do derivative of the outside first, meaning I'm going to bring the third power down, right? So power rule there, and I'm going to subtract 1 from the power. So I'm going to have 3 times 4/3 pi times r of t squared. Then I multiply by the derivative of the inner function. The inner function in that case is the r of t itself. So times r prime of t. Great. So now we have an equation that involves the unknown quantity that we're actually looking to solve for, right? Which is the r prime. So once you have that, you want to fill in everything else with numbers and isolate r prime. So I need to be able to fill in everything with numbers. Do I know, and this is where I'm going to ask for some participation in the chat, do I have a value that I can replace v prime with? $100, great. That's exactly right. We're given that v prime is 100, so I'll just plug in 100 there. So 100 equals, I can kind of simplify this stuff. The 3 will cancel there, so I just have 4 pi. Now, do I have a value that I can replace just r of t with? Am I explicitly given? Okay, Kai, why do you say 50?
because it's asking what the derivative or the rate of how fast the balloon radius is decreasing at 50 centimeters. So we're looking for the derivative at 50 centimeters.
You're right, except one thing. You're totally on the right track there, except that that's the diameter at 50. The diameter is 50 centimeters, right? So how does the diameter relate to the radius?
It's double, so it'd be 25.
Excellent. Good. So they don't directly give us the radius, but they give us the information where we can find the radius, right? So diameter is 50, so the radius is 25. So Kai's right. I'm replacing radius with 25, and that's squared. And then the only thing left is the r prime, and that's the thing I'm trying to solve for. All right, so we get 100 equals, what's 25 squared? 625? Times 4 is 25. So I have 100 equals 2500 pi times r prime. So r prime is equal to 100 over 2500 pi, which we're going to just approximate that to 0.013. All right, units. What should the units of r prime be? Remember, r is the radius, so the radius would be measured, in this case, in centimeters. What should the units of r prime of t be? Good. Excellent. So it would be centimeters per second. And there's our answer. All right, we got through our first related rates problem. This one's a classic. So we have a ladder 10 feet long resting against a vertical wall, and the bottom of the ladder is sliding away from the wall at a rate of 1 foot per second. How fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet away from the wall? All right, let me put my artistic skills to use here. There's my wall. It's perfectly drawn. Here's my floor. Now you guys are like, whoa, is that a photograph of a wall and a floor? Nope, it's just me drawing it. Okay, there's my ladder. The ladder is 10 feet, that's constant. Now that ladder is coming down the wall. So what's not constant is this distance between the top of the ladder and the side of the wall, right? That's shrinking. So I'm going to name that a variable. And since it's vertical, why don't we just call it y? So y is a function of time because it's changing over time, right? And since, same deal here, since the ladder is sliding down, the bottom is sliding this way, right? So that distance between the bottom of the ladder and the wall is also changing over time, so we're going to call that one x of t, since it's changing over time. Great. So now let's label some of the stuff that we have. or the information that we're given. The ladder slides away from the wall at a rate of 1 foot per second. What's a good notation for that 1 foot per second in the chat? What's a good notation for that? I'm really going to emphasize that word. I'm going to keep circling it until you give me a good notation for it. You guys aren't giving me a notation for it, and I'm putting exclamation points. What is the word rate indicating? Oh, you guys are going to do me like this. What's a rate? A rate of change. Derivative. Thank you, Dylan. Thank you, Emerson. Yes, it's a derivative. It's a derivative of what part of my diagram? What part are they talking about? It's sliding away from the wall. What's it the derivative of in my diagram? Away from the wall. Away from the wall. There we go. It's the derivative of x. So it's x prime, right? Good. So x prime of t equals 1 foot per second. How fast is the top of the ladder sliding down the wall? What's a good notation for that? How fast is the top of the ladder sliding down the wall? Maisie, what's a good notation? There we go. Y prime, right? That's what we're actually looking for. So what we want to know is y prime. Okay. So I need an equation that can relate x and y and maybe the length of our ladder as well. Is there an equation you guys can think of off the top of your head that relates those three things? Maybe developed by a crazy cultist mathematician from the Greek era who worshipped numbers and had a famous theorem named after him. He really liked triangles. There we go, Pythag. I agree. So we'll go x squared plus y squared equals the hypotenuse squared, so 10 squared, right? And so now we have an equation that relates the things that we're talking about. And all we need to do is get the derivatives involved. So what we're going to do at this point is differentiate both sides with respect to t. Let's start on the right-hand side. What's the derivative on the right going to be? What's the derivative of 10 squared? Don't you dare say 2 times 10 to the first power. That's what's up, Dylan. It's a constant. The derivative of a constant is 0. On the left-hand side, we are going to have to use the chain rule for both of these. So we're going to use the power rule to get the derivative of the outside. So I'm going to have 2 times x of t to the first power. Then I'll do the derivative of the inside function, which is x of t, so times x prime. And then same thing with y. We're going to get the exact same deal. 2 times y of t times y prime. Right? So in these related rates problems, once you've taken the derivative, your goal is to fill in values for everything but the thing you're trying to solve for, which is, for us, y prime. So everything else I want to be able to fill in some values for. Okay. So let's start here. 2 times, now right away I kind of run into a roadblock. I need x of t. Am I given a value from x of t? Go back to the prompt. Am I given a value for x of t? X of t would be the distance that the ladder is away from the wall. Awesome, Maisie. Yep, 6. I'm told that the bottom of the ladder is 6 feet from the wall, so I am given that. So x of t is 6. Do I know x prime of t? So look at the information we've written down. Do I know x prime of t? Good, Emerson, yeah. We wrote that down earlier. That's just right up here. X prime is 1. That's the rate that the ladder is sliding away from the wall, sliding away at 1 foot per second. So x prime is 1 plus 2 times. Now, do we know y of t? Y prime we don't need to fill in. That's what we're trying to solve for, but we do need to be able to fill in y. Ooh, Maisie. You're right, but how did you get that? I agree with you. It is 8. Yeah, that's right. So we're not directly given y, but we do know that x is 6. So we know that this side of the triangle is 6. We know the hypotenuse is 10. And so we can always just use Pythag to solve for that third side, right? We know that basically 6 squared plus y squared equals 10 squared. And then we can go ahead and solve for y. This is a Pythagorean triple. And it comes out with y equal to 8. Awesome. So now we filled in everything that we can. All that's left to do is just solve for y prime and throw some units onto it. So 2 times 6 is 12 plus 16 y prime equals 0. 16y prime is negative 12. Divide out the 16 and reduce y prime is negative 3/4. What units? What are my units going to be here? So y is measured in feet, right? Good, feet per second. Oh, what am I doing there? There we go. So it makes sense that it's negative because if you think about it, that this side of the triangle is shrinking as this side, the bottom side, increases, right? And so as we saw in our little group work from 4.3, if a rate of change is decreasing, it should be negative. All right. All right. So the last example we're going to do today is the College Board loves inverted circular cones for some reason. And I think I know why, because they involve similar triangles and they complicate things. So what's an inverted circular cone? It's an upside down cone. Water tank has the shape of an inverted circular cone with a base radius of 2 meters and a height of 4 meters. Water is being pumped into the tank at a rate of 2 cubic meters per minute. Find the rate at which the water level is rising when the water is 3 meters deep. First thing I'm going to do is diagram this. So let's draw our inverted circular cone. Great, there it is. So you got your water being pumped into the tank. I'm going to put my water right here. And you can see that we're talking about a volume, right? So they're giving us a rate that the volume is changing. So it's 2 cubic meters per minute. Whoa. So right away, that's a rate of change for volume. So I'm going to call that, well, hold on, let me get some participation in the chat. What's a rate of change for volume? When I say rate of change, what do I want you thinking? Derivative. That's right. So this is a derivative they're talking about. So we want to give it a derivative notation. So I'm going to call it V prime of t. And that's 2 cubic meters per minute. And they want us to find the rate at which the water level is rising. So they want us to find the rate that that is changing. I'm going to call that h of t, just for height, okay? So the rate at which the water level is rising then would be h prime of t. And that's the thing that we're looking for. So, all right, I need to come up with an equation that involves volume and height. Does anybody know the volume formula for a cone off the top of their heads? Well, I'll tell you what it is. The volume of a cone, 1/3 pi r squared h. There we go. That's going to be our formula that we use. You can clearly see that that does relate the volume and the height. All right, so let's rewrite this to be functions of time, because some of these things are changing over time. And what I want you to remember is, yes, we have our tank is an inverted circular cone, but as we pump water in, the water itself is also going to be in the shape of an inverted circular cone, right? And that cone is just going to be getting bigger as the water gets pumped in. So when I talk about that volume formula, I'm specifically referring to the volume of water here. So what's changing over time? The volume of water is definitely changing over time. The radius of the water, so this, right, as the volume increases, that radius is going to be getting bigger. So that's a function of time. And the height of the water is also changing over time. All right, so this one's a little trickier because normally in the past two examples, once I've written the equation, right, that relates my two variables of interest, I would then differentiate. I can't differentiate yet because I have three variables here, right? We have the volume, we have the radius, and we have the height. And before we take the derivative, we want to get this only in terms of our two variables that we're given information about, which is v prime and h prime. So I kind of want to get rid of that radius. And this is why the College Board loves right circular cones. Because when we look at a right circular cone from the side, and we cut it in half like this, what we end up with is similar triangles. Can you guys see the two triangles I'm talking about? We have this big triangle. Here, that's a right triangle. And then we have my inside triangle here, which is also a right triangle. And these are similar, meaning they're proportional. And what we can do with similar triangles is create a proportion, so an equation. And we're going to do that because they tell us some information about this cone. They tell us that its base radius is 2. That means at the top, at the base, I should say, we have a 2-meter radius there. And the height, so this, is 4 meters. And so what I can do is create a proportion. And the proportion I'm going to create, I'm going to go the small side of this triangle over the small side of the big triangle. So I'll say r over 2 equals the small side of the pink triangle, which is h, equals h over, I'm sorry, the big side, the big leg of the pink triangle over the big leg of the green triangle, so h over 4. And then I can solve for r, just multiply the 2 over. R equals 2h over 4, or h over 2. And that allows me to make a direct substitution. I can just replace the radius in my volume formula with h over 2. All right? So now I get v of t equals 1/3 pi. And instead of r, I'll have h of t over 2 squared times h of t. That's great. So now I have this volume formula in terms of only the height, which is the thing I'm looking for. That's why I put it in terms of the height, right? And before I do calculus with this, let's just simplify it. So volume is 1/3 pi times h of t squared over 4 times h of t. All right, I'm just going to pull this 4 out and multiply it here to make 1/12. And then I'll just put the pi over that 1/12. So pi over 12 equals, oh God. V of t equals pi over 12 times h of t quantity cubed. So I told you, these problems are long, but not the calculus part. It's like the parsing it, the setting it up, the getting it ready to do calculus. And now we can do calculus. And this is the short part, right? This is the straightforward part. We'll differentiate both sides with respect to time. On the left-hand side, we just end up with v prime. Right-hand side, we got to use the chain rule to evaluate this. So we're going to bring the 3 down. So I have 3 times pi over 12 times h of t squared. Then multiply by the derivative of the inner function, which the inner function is h of t, so times h prime. All right. Once you've taken the derivative, you want to plug in values for everything but the unknown you're trying to solve for. So do I have a value for v prime? Do I know what v prime is? 2? Good. So 2 equals, whoops, that's 3 pi over 12, not 3 pi over 2. So that 3 pi over 12 can reduce to pi over 4 times. Do I have a value for h of t? Is there a value I can plug in for h of t? Good, Maisie. Yeah, I agree. That's what this information is. They want to know when the water is 3 feet deep. So that's when the height is 3 feet, right? 3 meters, rather. Not feet. So times 3 squared times h prime. And now our goal is just to solve for h prime. So 2 equals 9 pi over 4 times h prime. And then multiply by the reciprocal. H prime is 4 over 9 pi times 2. Probably going to want to give an approximation of that. So that's 8 divided by 9 pi. And that's about 0.283. And that would be in units of meters per minute in this case. So yeah, just to clear up, Emerson had put 4, and you just want to be careful in that last step, right? They do tell us that there's a height of 4, but that's the height of the entire tank. We want to know how fast the water is rising when the water is 3 meters deep, which is the height that we're talking about for this formula. Okay, I think that's all the examples I have for today.